Right now, beneath the soles of your feet, an ocean of liquid metal is moving in ways that are throwing off the most precise clocks humanity has ever built. The planet you are standing on has started spinning faster than it has in the entire history of accurate measurement. Days are quietly getting shorter. The magnetic shield that keeps the worst of the sun off your skin is weakening. And there is a vast region over the southern Atlantic where that shield has already grown alarmingly thin. And the great river of warm water that keeps an entire continent livable is slowing down. None of these things are rumors. They are measured, confirmed, published, and watched in real time by instruments that do not exaggerate and do not panic. This is why a single shortened day, a difference so small you could never feel it, sent a quiet ripple of unease through the people who keep global timekeeping running. Because when a world that is 4.5 billion years old suddenly changes its oldest, steadiest rhythm, the small number on the readout is never really the story. The story is what is causing it, and how many other systems are changing at the same time. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath, and let's begin. On the 29th of June, in the year 2022, the planet did something it had never done before in the era of atomic timekeeping. Earth completed a single full rotation faster than at any moment scientists had ever recorded with that level of precision. The day came up short by 1.59 milliseconds. That sounds like nothing. It is a sliver of time so thin that no human nervous system could ever register it. A blink lasts 100 times longer. To put it another way, in the span of that missing fraction, a beam of light would barely have time to circle a portion of the planet. It is far too brief for any sense we possess to detect. It is shorter than the time it takes a single thought to form, shorter than the briefest sound you could make. If someone could reach into your day and quietly remove that much time, you would live the rest of your life never knowing it had happened. And yet, to the people whose job is to watch the rotation of the planet, that tiny shortfall was extraordinary. Because a world this old does not casually rush through its own day. It has a baseline, a deep and ancient habit. And for almost all of recorded history, that habit ran in one direction only. And when it happens not once, but again and again, across multiple years in a row, the question quietly shifts. It stops being, "Is this real?" and becomes, "What on earth is driving it?" To picture what a faster spin actually means, set aside the digital numbers on a screen for a moment and imagine the planet itself as a clock. Not a clock on a wall, but the whole turning world, completing one full revolution roughly every 24 hours. That 24-hour day is not a fixed and sacred number. It never was. The rotation of the Earth has always wavered, speeding and slowing by tiny amounts, responding to a tug here and a shove there, from forces both inside the planet and far beyond it. No one noticed for most of history, because there was no instrument steady enough to catch such tiny variations. The day simply was the day, the unquestioned measure against which everything else was set. Only when clocks grew precise enough to outdo the planet did these small wanderings come into view. And with them the realization that the length of the day is not a fixed quantity at all, but a living number that breathes and shifts from one year to the next. For nearly all of recorded history, the overall drift was towards slowing. But around the middle of the previous decade, that ancient drift reversed, and the planet began, ever so slightly, to hurry. For most of the time humans have been keeping track, the planet has been slowing down. The moon is the reason. It pulls on the oceans, raising tides that drag against the turning crust like a soft, endless break. Across vast stretches of time, that gentle drag has been stealing rotational speed from the planet, fraction by fraction. We can actually read this in stone. Ancient coral fossils, hundreds of millions of years old, preserve daily and yearly growth bands, like the rings of a tree but finer. Count them, and the message is clear. Around 400 million years ago, a single year held more than 400 days. The days were shorter back then, because the planet was spinning faster, and the long, patient pull of the moon had not yet had time to slow it. Think about what that really means. A creature alive in those ancient seas, had it any way of knowing, would have experienced a day noticeably shorter than ours. The sun would have raced across the sky a little quicker. The nights would have arrived a little sooner. And the moon, the very thing slowing us down, sat much closer to the earth in those days, looming far larger in the sky than the modest disk we see now. Every year, the moon drifts a few centimeters farther away, carried outward by the same tidal exchange that steals the planet's spin. It is a slow, grand bargain, written into the laws of motion. The moon takes a little of the Earth's rotational energy, and in return it climbs to a slightly higher, slightly more distant orbit. Over hundreds of millions of years, this has lengthened our day and widened the moon's orbit. In lockstep, a single connected process unfolding across almost unimaginable spans of time. And it continues, quietly, to this day. The moon is still drifting away from us, a few centimeters every year, about the rate at which your fingernails grow. In the deep future, billions of years from now, the day will have grown far longer than the 24 hours we know, and the moon will hang smaller and more distant in the sky. This is the grand, slow direction in which the planet has been traveling for almost its entire history, the steady lengthening of the day under the patient hand of the moon. It is the backdrop against which the recent acceleration stands out so sharply. For the planet to be speeding up at all, something must be pushing against this ancient, relentless slowing and pushing hard. So the expected direction of travel is deceleration. Slow, steady, predictable lengthening of the day across geological time. Which is exactly why what began to happen around the year 2016 made researchers stop and look twice. The trend reversed. Earth started speeding up, not violently, not in any way you would notice in your morning routine, but measurably and stubbornly. Year after year, the planet began logging some of the shortest days ever captured by modern instruments. The year 2020 set a record at the time, with a day shorter than any before it. The year 2021 stayed nearly as fast, the planet holding its quick new pace. Then, the year 2022 shattered the record outright, with the shortest day ever captured in the atomic age. And the trend did not simply stop there. The years that followed continued to deliver some of the shortest days ever measured, as if the planet had settled into a new and faster habit. Each time the record fell, the people who track these things took notice, because a single anomalous day could be dismissed as a fluke, the result of some passing storm or shift in the winds. But a pattern stretching across year after year is not a fluke. It is a signal. And here is the part that turns a curiosity into a genuine puzzle. The forces that cause the slowing have not gone anywhere. The moon is still there. The tides are still dragging. The brake is still on. Yet, something else has begun pushing in the opposite direction, hard enough to overpower the brake and send the planet spinning faster anyway. That is, the mystery. And the suspects are scattered across every layer of the world, from the thin film of air above your head all the way down to the searing heart of the planet. At the surface, melting ice is rearranging where the planet's mass sits. In the atmosphere, shifting belts of pressure shove against the rotating crust. In the oceans, the patterns of the great currents tighten and slacken, applying their own subtle push and pull. The atmosphere alone is a remarkable player in this drama. It seems almost absurd that something as light and insubstantial as air could influence the spin of a planet weighing as much as the Earth. And yet the atmosphere is not nothing. It is a vast envelope of gas, and when the winds of the world blow harder in one direction, that moving air carries rotational motion with it. By one of the deepest rules of physics, if the atmosphere gains rotational motion, the solid Earth beneath it must lose an equal amount, and the reverse holds too. So when the great jet streams strengthen, the planet beneath them slows by a flicker. When they ease, the planet speeds back up. This handoff happens on the rhythm of the seasons, as the winds of the northern and southern halves of the world trade dominance through the year. It happens during the great climate swings of the Pacific, when warm and cool phases reshape the winds across an entire ocean. The atmosphere and the solid Earth are locked in a constant, gentle exchange of motion, trading spin back and forth, and the atomic clocks read every transaction. The oceans add their own contribution, sloshing and circulating, their immense weight-shifting position as currents speed and slow. The planet, in other words, is not a single rigid object turning smoothly in the dark. It is a layered, fluid, restless thing, with its air, its seas, its molten metal, and its solid heart all in motion, all trading energy with one another. And the length of the day is the sum of that whole churning conversation. And deep below everything, more than 2,900 kilometers down, a churning sea of molten iron moves in ways that are coupled, directly and physically, to the spin of everything above it. Each of these forces is real. Each one is measurable, and each of them, on its own, is far too feeble to make a difference you could ever notice. The genius and the difficulty of this science lies in measuring the almost unmeasurable. A single great storm, redistributing the weight of the atmosphere across thousands of kilometers, can change the length of the day by a fraction of a millisecond. The seasonal march of the winds, blowing harder one half of the year than the other, makes the planet speed up and slow down on a yearly rhythm that the atomic clocks catch with ease. When a powerful current shifts in the Pacific, warming and cooling vast stretches of ocean, the day length responds. When a truly enormous earthquake strikes, rearranging a portion of the planet's mass in an instant, the spin can change in a way that is small but real and permanent. All of these whisper into the length of the day, and the atomic clocks hear every one of them. What scientists are still untangling is how they fit together, which of them is in charge right now, and whether the acceleration is building towards something or quietly approaching a turn. What is not in doubt is the simplest and strangest fact of all. The planet is not behaving the way the models said it should, and that, in the end, is what makes this worth paying attention to. A model is a kind of promise about how the world will behave, built from everything we have learned about it. When the world keeps that promise, we barely notice the model at all. When the world breaks it, the model becomes a question, and the question points us towards something we did not understand. The faster spin is exactly such a broken promise, a sign that the planet holds processes we have not fully accounted for, processes now making themselves felt at the surface. And the systems we built to keep time, to guide our satellites, and to hold global infrastructure in step with one another were all designed around a slower world. They are now running slightly behind reality. And the gap between the time kept by atoms and the time kept by the turning Earth is forcing a decision that the engineers who keep the internet alive describe as one of the most dangerous things that could ever be asked of them. To understand why a single millisecond can matter, you first have to understand the instrument sensitive enough to catch it. For thousands of years, humanity measured time by the sky. The rising and setting of the sun marked the day. The slow march of the stars marked the seasons. The phases of the moon marked the months. Every clock ever built, from the shadow of a stick to the swing of a pendulum, was ultimately just a way of subdividing the turning of the heavens into smaller and smaller pieces. And the turning of the heavens was, in truth, the turning of the earth. The planet itself was the master clock, and everything else was a copy, calibrated against the steady wheel of day and night. For all that time, no one could ask whether the Earth itself was a good clock, because there was nothing more reliable to measure it against. That changed completely in the middle of the previous century, with an invention that finally gave humanity a timekeeper steadier than the planet beneath it. Before the middle of the 1950s, the finest clocks on Earth drifted by about 1 second every 300 years. That sounds astonishing. By the standards of any earlier century, it was almost miraculous, but it was not nearly good enough for what was coming. The breakthrough came from looking not at gears or pendulums, but inside a single atom. Certain atoms, when nudged with the right energy, vibrate at a frequency so stable, so utterly reliable, that it never changes. The cesium atom is the favorite. An electron inside it flips between two states at a rate that is fixed by the laws of physics themselves. Count those flips, and you have a clock that does not care about temperature, or gravity, or the weather, or the age of the machine around it. The official definition of a single second is now tied to this. 1 second is the time it takes for a cesium atom to oscillate 9,192,631,770 times. That is not an approximation. That is the definition. Stop and consider how profound that shift was. For all of human history before this, the second had been a child of the day, simply the day chopped into ever finer pieces. The day defined the second. Now the relationship was turned upside down. The second was defined by the unchanging heartbeat of an atom, anchored to a constant of nature that does not vary from one place to another or 1 century to the next. The day, the turning of the entire planet, was no longer the source of time. It had become just another thing to be measured against the atom, and found, to everyone's quiet surprise, to be slightly unreliable. A clock built on this principle can run for tens of millions of years without losing a single second. The very best of them are now so precise they would not drift by 1 second over a span longer than the age of the universe. It is worth pausing on just how alien that level of precision is to ordinary human experience. We live our lives in seconds and minutes, in the time it takes for a kettle to boil or a traffic light to change. The idea of a device that could run from the formation of the planet until today and still be accurate to within a fraction of a second is not something the human mind was built to hold. And yet that is the tool we now use to keep the modern world in step. The first of these atomic clocks were enormous, delicate machines, housed in laboratories and tended by specialists. Over the decades they shrank, and steadied, and multiplied. Today there are networks of them, scattered across the globe, in national laboratories on nearly every continent, and their readings are constantly compared and averaged together. No single clock is trusted on its own. Instead, the world keeps time by taking a weighted average of hundreds of these atomic timekeepers, blending their voices into one steady, official measure of the second. That blended measure is the heartbeat of the modern age. It is the reference against which the spin of the planet is now judged and found, ever so slightly, wanting. And tracking the planet against that reference is a discipline all its own. Scientists combine the readings of the atomic clocks with measurements of the Earth's actual orientation in space, taken by pointing radio telescopes at distant, ancient beacons billions of light years away, objects so far off that they appear utterly fixed. By measuring the planet's position against those fixed points, again and again, They can determine exactly how the Earth is turning, down to fractions of a millisecond. It is by comparing this measured turning against the steady tick of the atomic clocks that the speeding up was caught in the first place. Two of the most precise measurement systems ever devised, the atomic clock and the network of radio telescopes, working together to watch a single planet spin. It is worth pausing on the strangeness of that arrangement. To measure how fast the Earth turns, scientists look outward, to objects so unimaginably distant that their light has been traveling toward us since long before the planet existed. Against those far-off, seemingly motionless beacons, the slow rotation of the Earth can be tracked with breathtaking precision. We use the most distant things in the universe to measure the most familiar one beneath our feet. The far away and the near, the ancient and the immediate, joined together in a single measurement that catches the planet quietly speeding up. And here is where the strangeness begins. Once you have a clock that perfect, you suddenly have something to compare the planet against. For all of history before this, the spinning Earth was the master clock. The sun rose, the sun set, and that was time itself. There was nothing more accurate to check it against. The atomic clock changed that relationship completely. For the first time, humanity had a timekeeper steadier than the planet. And when scientists held the two side by side, they could finally see the truth that had always been hidden. Earth is not a perfect clock. It wobbles. It speeds up and slows down by tiny amounts all the time, responding to forces from above and below. The atomic clock does not move. The planet does. So the drift everyone now talks about is not the clock failing. It is the clock revealing. And what it has revealed, across the last decade, is a planet quietly breaking its oldest pattern. There is something almost poetic in that reversal of roles. We built the atomic clock to serve us, to be the most faithful servant of time we could imagine. And the moment it became more faithful than the planet itself, it turned around and told us something we had never been able to learn before. That the ground beneath our feet, the great wheel we had trusted to mark time for the whole of our existence, was never quite as steady as we believed. The clock did not break our trust in time. It deepened our understanding of the world. Now think about what depends on perfect time. Picture a single enormous spinning wheel. Every gear attached to it, every linked piece of machinery, is calibrated to turn at one shared rate. Speed the wheel up, even slightly, and nothing snaps in the first instant. But every connected part slowly slides out of step with the timing it was built around. The longer the mismatch runs, the further everything drifts, and the further it drifts, the more strain builds on the joints, holding the whole thing together. This is the hidden truth about the modern world that almost no one thinks about as they go about their day. The entire structure of contemporary life, the things that feel solid and permanent, is held together not by steel or concrete but by agreement about time. Every transaction, every signal, every coordinated action across the globe assumes that all parties share the same instant, the same now. That shared now is not a law of nature. It is something humanity built, painstakingly, by linking precise clocks across the world into a single agreed measure. And it works only so long as the foundation it was built on, the predictable turning of the planet, stays predictable. The rotation of the planet is that wheel. The connected parts are everything we have built that runs on precise time. And the drift, though it begins as something far too small to feel, does not stay small. A single shortened day means nothing in isolation, but the days do not change in isolation. They change together, in the same direction, accumulating quietly over months and years until the gap between the time kept by atoms and the time kept by the turning planet grows wide enough to demand a response. A millisecond here and a millisecond there. gathered across hundreds of days, becomes a full second of difference, and a full second is the threshold at which the keepers of global time must act. That is how something far too small to feel becomes something large enough to force a decision that could ripple across the digital world. Take the satellites that tell you where you are. They orbit far overhead, broadcasting signals timed to billionths of a second, and they are synchronized to atomic time, not to the spin of the Earth. The way these satellites work is itself a quiet marvel. Each one carries its own atomic clock, and each constantly broadcasts the exact time according to that clock. A receiver on the ground, in your phone or your vehicle, listens to several satellites at once, and by comparing the tiny differences in when each signal arrives, it calculates its own position with remarkable precision. The entire system is, at its heart, a machine built out of time. Distance is measured by timing, and timing is everything. This means the satellites must agree, perfectly, on what time it is. And they must agree with the ground-based systems that translate their signals into a position on a map of the turning Earth. That map assumes the planet rotates in a known and predictable way. When the planet turns slightly faster, the ground moves ahead of where those satellites expect it to be. The error is not measured in kilometers. It is measured in centimeters. But in aircraft navigation, in surgical robots, and in self-driving systems, centimeters are the difference between right and catastrophically wrong. Consider what the modern world quietly trusts to those signals from above. When an aircraft descends through thick cloud toward a runway it cannot see, it leans on precise positioning to know exactly where the ground is. When a surgeon guides a robotic instrument through delicate tissue, the machine must know its own position to a hair's breadth. When a self-driving vehicle decides whether the shape ahead is in its lane or the next one over, the answer can hinge on a handful of centimeters. The phones in our pockets, the ships crossing the oceans, the tractors plowing fields in dead straight lines, the emergency crews racing to find someone lost, all of them depend on a quiet agreement between the satellites overhead and the turning ground below. And that agreement is built on the assumption that the planet turns in a known, predictable way. When the planet quietly changes its spin, that assumption begins to fray, and the corrections required to keep everything aligned grow more frequent and more delicate. The financial world is another layer of the same machine. The great stock exchanges execute millions of trades every second, and each one carries a timestamp accurate to a millionth of a second. Those timestamps are anchored to a single shared global time, which is itself anchored to atomic clocks. A planet out of sync produces timestamps out of sync, and in the fastest corners of trading, a single microsecond of ambiguity can represent a staggering amount of money. In these markets, computers buy and sell in the time it takes a beam of light to travel a short distance down a wire. Firms have spent enormous sums laying the straightest, shortest possible cables between trading centers, shaving microseconds off the time it takes a signal to travel, because those microseconds translate directly into advantage. In a world that's competitive, the exact order in which two events happened matters enormously, and the order is determined entirely by the timestamps. If those timestamps become uncertain, even by the smallest sliver, the question of who acted first, and therefore who is owed what, can blur into confusion. The entire structure rests on the quiet assumption that time is a single, shared, perfectly ordered thing. Disturb that assumption, and the disputes that follow are measured in fortunes. Power grids may be the most physical example of all. Alternating current flows at a fixed rhythm, 50 or 60 cycles every second depending on the country, and grid operators lean on shared global time to balance the enormous flow of power across entire regions. When time drifts, that balancing act drifts with it. A power grid is a constant, invisible juggling act, matching the electricity being generated to the electricity being used, instant by instant, across vast distances. If the supply and demand fall too far out of step, the consequences are not abstract. Frequencies wander, equipment strains, and in the worst cases, protective systems trip and entire regions fall dark. Operators rely on perfectly synchronized time to coordinate this dance across hundreds of power stations and thousands of kilometers of cable. When the shared sense of time becomes uncertain, the margin for error in that delicate balancing act shrinks. Now, here is the layer almost nobody thinks about. All of this was already being managed. Scientists knew long ago that the planet was an imperfect clock. That is exactly why, back in the year 1972, they invented something called the leap second. Whenever the gap between atomic time and the turning Earth grew too wide, they would simply add 1 extra second to the official clock, nudging it back into step. It was a patch, a small, occasional correction. The system was clever in its simplicity. Rather than try to force the precise atomic clocks to match the slightly imperfect planet, or force the planet to behave, which is plainly impossible, the keepers of time simply agreed to occasionally insert an extra second into the official record. When the gap between atomic time and the turning of the Earth approached a certain threshold, the world's timekeepers would announce that a particular minute would, for once, contain 61 seconds instead of 60. For one strange instant, clocks around the world would display a time that normally does not exist, and then carry on as if nothing had happened. It was an elegant compromise between the perfection of the atom and the imperfection of the planet. And here is the telling detail. Since that system began, 27 leap seconds have been added. Not a single one has ever been removed. The reason is simple. The planet was always slowing down, which meant the atomic clocks were always running a little ahead, which meant the fix was always to add time. Always to add. But now the planet is speeding up. Now the atomic clocks are the ones falling behind. And for the first time in the entire history of this system, the conversation has flipped to something that has never been done. Removing a second from the official clock. A negative leap second. And the engineers responsible for the backbone of the internet have said, plainly and on the record, that this is one of the most dangerous things that could happen to global digital systems. These are not people given to drama. They spend their careers keeping vast, invisible systems running smoothly, anticipating problems most of us never even imagine. When people in that profession describe something as among the most dangerous things they can foresee, it is worth taking seriously. Their concern is not that a single second is a large amount of time. It is that the systems they tend have been built, layer upon layer, over decades, on an assumption so basic that it was never even written down as a rule. That time moves forward. To ask those systems to accept a moment where time steps back is to test an assumption so deep that no one can be fully certain what will happen when it breaks. A single second taken backward. The trouble is that the systems running the modern world were never taught how to go back. For half a century, every correction moved the clock forward, and so every piece of software, every protocol, every safeguard quietly assumed that time only ever flows in one direction. Subtracting a second asks all of them to do something they were never designed to do. To watch the clock tick to a moment, and then watch that moment arrive a second early, as if a sliver of time had simply been deleted. When the leap second was first added, decades ago, the digital world was small and forgiving. A handful of machines stumbled, a few systems hiccuped, and the damage was easily contained. But the world has changed beyond recognition since then. Every added leap second in recent memory has caused problems somewhere. Major websites have gone down. Airline booking systems have frozen. Networks that span the globe have tripped over that single extra second because deep in their code lurked an assumption that the minute would always contain exactly 60 seconds, never 61. And those were the easy cases, where time moved forward in the familiar direction, just with one extra tick. A negative leap second has never been attempted, not once in the entire history of the system. There is no real-world experience to fall back on. There are countless systems that have simply never been tested against a clock that runs backward, because until now, there was never any reason to imagine it would. In a world stitched together by timestamps, where one event must always come after another, a clock that suddenly runs backward can convince a system that an effect happened before its cause. That is the kind of contradiction that can crash networks, corrupt records, and cascade through connected systems faster than any human can intervene. Imagine a system that records two events, one after the other, and trusts that the second always carries a later time than the first. Now imagine the clock stepping backward in the moment between them, so that the later event appears, by its timestamp, to have happened before the earlier one. To a human, the absurdity is obvious. To a machine following rigid rules, it is a genuine paradox, the kind that can send it into an endless loop, or freeze it entirely, or quietly write false information into permanent records that other systems will later trust. And because so many systems are linked, the confusion in one can spread to the next and the next, faster than any engineer could trace it. This is why the people who safeguard the backbone of the internet speak of a backward second with such unease. It is not the size of the change that frightens them. It is that the change moves in a direction the digital world has simply never been built to survive. And the only reason this nightmare is even being discussed is the thing happening deep inside the planet, pushing it to spin faster. So now we go down, past the crust, past the mantle, into the strangest engine in the world. It is a journey no machine could ever truly make, a descent through conditions so extreme they defy ordinary intuition. And yet everything we find down there is bound by the unbreakable laws of physics to the length of the day you live by at the surface. The Earth is not a solid ball. It is layered, like an onion built from fire and stone. At the surface sits the crust, the thin, brittle shell we live on, thinner in proportion than the skin on an apple. Everything in all of human history has happened on this fragile rind. Every city, every forest, every ocean, every mountain range, the whole theater of life sits on a skin of rock so thin that, if the planet were shrunk to the size of a fruit, you could scrape it away with a fingernail. Beneath that skin, the world is almost entirely a realm of heat and pressure that no living thing will ever visit. Below, that lies the mantle, a vast region of hot rock that flows over long stretches of time like incredibly slow, glowing taffy. It is solid to the touch, in the sense that you could not swim through it, and yet across millions of years it churns and circulates, carrying heat upward from the depths in enormous, ponderous loops. This slow churning is what drives the drifting of the continents, the building of mountains, and the trembling of earthquakes at the surface. The ground we think of as the very definition of stability is, on a long enough view, riding on a sea of creeping stone. And below the mantle, beginning about 2,900 kilometers down, the world changes completely. There, the rock gives way to metal. This is the outer core, an immense ocean of liquid iron and nickel, hotter than the surface of the sun, swirling under pressures that would crush anything from the surface into nothing. The temperatures down there are staggering. climbing toward 5,000 degrees and beyond, rivaling the glowing face of the sun itself. And yet, because of the unimaginable weight of the entire planet pressing inward, this metal does not behave the way molten iron would in a foundry on the surface. It is a fluid, but a dense and exotic one, flowing in slow, vast spirals across distances of thousands of kilometers. It is here that one of the most important processes in the entire planet takes place. As this molten metal churns, driven by heat escaping from below and by the spin of the planet itself, it generates electric currents. And those currents generate a magnetic field, wrapping the entire world in an invisible shield. This is the dynamo, the beating heart of Earth's magnetism, and it is the reason life on the surface has survived at all. The process is a marvel of self-sustaining physics. The motion of the conducting metal generates electric currents. Those currents generate magnetic fields, and those magnetic fields, in turn, shape the way the metal flows, reinforcing the very currents that created them. It is a loop that feeds itself, a great natural engine that has run, with interruptions, for billions of years, powered by the slow leak of heat from the planet's core into the cold of space. As long as the core stays hot enough to keep the metal churning, the dynamo turns and the shield holds. This is why the size of a planet matters so much for whether it can hold on to a magnetic field. A small world cools quickly, its internal heat radiating away into space, until the core grows still and the dynamo dies. A large world like the Earth holds its heat for billions of years, its core staying molten and restless far longer, keeping the dynamo alive across spans of time that dwarf the entire history of life. We owe the shield over our heads, in part, to the simple fact that our planet is large enough to have stayed warm inside for 4.5 billion years. Had the Earth been much smaller, its dynamo might have faltered long ago, and the story of life on its surface might have ended before it truly began. But it is not a calm or steady engine. It is turbulent, chaotic, full of swirls and surges, and the field it produces is forever shifting, drifting, and occasionally tearing itself apart and rebuilding in a new configuration. Everything we see at the surface, the wandering poles, the weakening field, the dent over the Atlantic, is the distant expression of that churning, restless engine far below. Go deeper still, past the liquid, and you reach the strangest part of all, the inner core, a solid ball of almost pure iron, roughly the size of a small planet in its own right, sitting at the very center of everything. It is solid, even though it is hotter than the molten metal surrounding it, because the pressure there is so unimaginable that the iron cannot melt. Picture that paradox for a moment. Here is metal hot enough to be liquid, hotter even than the molten ocean wrapped around it, and yet it stays solid, frozen not by cold but by sheer crushing pressure. The weight of the entire planet presses inward on that central ball with a force so colossal that the iron atoms are squeezed into a rigid lattice and cannot break free into a liquid, no matter how hot they become. It is a kind of fire frozen into stone, the strangest object in the world hidden at its very center. And remarkably, this solid heart is slowly growing. As the planet very gradually loses heat to space across the eons, a little more of the surrounding liquid iron freezes onto the inner core each year, and the solid ball inches outward, fraction by fraction, across the depths of geological time. That slow freezing actually helps power the dynamo above it, releasing energy that drives the churning of the liquid metal and helps sustain the magnetic shield. The heart of the world is not a dead, inert lump. It is an active, evolving engine, and our existence on the surface is bound up with its quiet, hidden work. Every freezing layer of iron, every spiral of churning metal, every flicker of the field above, is part of a single, ongoing process that has run since the planet was young and will run until it finally grows cold, billions of years from now. We owe our atmosphere, our shield, and the steady spin we built our lives around to that distant engine, turning in the dark at the center of everything. It hangs there, suspended in the heart of the world, free to turn at its own pace inside the liquid ocean that surrounds it. And it is this hidden iron heart, more than anything else, that may be behind the planet's strange new spin. For decades, scientists believed something remarkable about this inner core. They believed it was spinning, very slightly, at a different rate than the rest of the planet. A separate rotation, hidden a planet's width beneath our feet, turning a touch faster than the ground we walk on. Because the inner core is locked away, no one can see it. No instrument can be lowered to it. Everything we know about it comes from a kind of cosmic eavesdropping. When a large earthquake ruptures somewhere on Earth, it sends waves of energy racing through the entire planet, like the ringing of a vast bell. Some of those waves pass straight through the deep interior, brushing past the inner core, and they emerge on the far side carrying the faint imprint of everything they touched. By comparing earthquake waves from the same kind of source, decades apart, scientists can read the changes in the iron heart the way a doctor reads the rhythm of a pulse. The technique is extraordinary when you think about it. There is no way to drill to the center of the Earth. The deepest hole humanity has ever bored reaches barely 12 kilometers down, a pinprick that does not even pierce the crust, let alone the thousands of kilometers of mantle and metal below. We will almost certainly never send an instrument to the core. The pressure and heat would obliterate anything we could build. And so the only way to study the heart of the world is to wait for the planet to ring like a bell, and to listen, with great care, to the echoes. Particular fault zones tend to produce earthquakes with remarkably similar signatures, again and again, across the years. These repeating quakes are precious, because they let scientists send what is effectively the same probe through the deep earth at different moments in time, and watch how the echo changes. If the path through the core has shifted, even slightly, the timing and shape of the wave that emerges on the far side will shift with it. It is a kind of slow-motion sonar, played out across decades, using the violence of the planet itself as the source of sound. And in the early years of the 2020s, that reading delivered a genuine shock. The inner core appeared to have slowed. Researchers studying these waves found evidence that the separate spin of the inner core had not just slowed relative to the surface, but may have actually paused, and possibly even begun, very gently, to turn the other way relative to the rest of the planet. The finding made headlines around the world, and it was often badly misunderstood. People imagined the center of the Earth grinding to a halt, with catastrophe to follow. That is not what happened, and it is worth being very clear about it. The inner core has not stopped. The planet has not stopped. What the evidence pointed to was something far subtler and, in its own way, far more interesting. This does not mean the center of the Earth stopped dead. The whole planet still spins as one, every single day. What it means is far subtler. The tiny difference in speed between the iron heart and the world around it appears to have wound down to nothing and then started to reverse. Like two dancers who have been turning at slightly different rates for years, slowly drifting back into the same step and then beginning to lean the other way. To be precise about what is being measured, the difference is tiny. Over the course of a year, the inner core might shift its position relative to the surface by only a fraction of a degree. It is not racing. It is not lurching. It is the gentlest possible drift, detectable only because the instruments are so sensitive and the records stretch back so many decades. But gentle as it is, that drift carries enormous mass, the entire iron heart of the planet. And even a whisper of change in something so massive can ripple outward into the spin of the whole world. And this may be part of a long, slow rhythm. Some researchers suspect the inner core swings back and forth in its relative spin on a cycle lasting many decades, perhaps around 70 years from one extreme to the other. If that is true, then we are living through one of these turning points right now. A moment when the deepest part of the planet quietly changes the direction of its drift. It is a humbling thought. There is a rhythm at the center of the Earth, a slow swing lasting longer than most human lives, and it has been turning quietly beneath every generation that has ever lived, entirely unnoticed until the last few years. Every empire that has risen and fallen, every story ever told, every life ever lived on the surface, unfolded above this hidden pendulum of iron, swinging back and forth across the decades. And only now, with instruments precise enough to catch the faint echoes of earthquakes passing through the deep earth, have we begun to sense its motion at all. It changes how you think about the ground beneath your feet. We tend to imagine the center of the Earth as the very definition of permanence, a still and unchanging anchor at the heart of everything. The reality is the opposite. The center of the Earth is one of the most dynamic places in the entire planet, a realm of flowing metal and a turning iron heart, never quite at rest, always shifting in ways that reach all the way up to the surface and into the clocks we keep. The most stable thing we can imagine turns out to be quietly restless, and that restlessness is part of the story of why the days are growing short. The reason this matters so much for the length of the day comes down to one of the most fundamental rules in all of physics. In a spinning system, the total amount of rotational motion is conserved. It cannot simply vanish. If one part of the system slows down, another part must speed up to make up the difference. This is not a quirk of the Earth. It is one of the great conservation laws that govern the entire universe, holding true for spinning galaxies, for collapsing stars, for the tiniest spinning particles, and for the planet beneath your feet. Motion of this kind is never created from nothing and never destroyed into nothing. It can only be passed from one part of a system to another, like a debt that must always be balanced. And so, if the deep iron heart of the planet sheds some of its spin, that motion does not simply disappear into the void. It has to go somewhere. It is handed off to the rest of the world. Picture a figure skater spinning with arms outstretched, then pulling those arms in tight to the body. The skater speeds up, dramatically, without any extra push, purely because the same rotation has been pulled inward. It is one of the most beautiful demonstrations in all of physics, and anyone who has watched the sport has seen it. The skater does no extra work, exerts no extra effort to spin faster. They simply move mass closer to the axis they are turning about, and the spin quickens on its own, because the total amount of rotation must be preserved. Pull the arms in, and the spin accelerates. Spread them out, and it slows again. This is not a trick or an illusion. It is one of the deepest and most unbreakable rules in the universe, and it applies to spinning skaters, spinning stars, and spinning planets alike. Now imagine that exchange happening between the iron heart of the planet and everything wrapped around it. If the inner core gives up some of its relative spin, that motion does not disappear. It is handed off, through the liquid metal and the mantle, to the rest of the world. And the rest of the world, receiving that gift of motion, turns just a little faster. The day grows just a little shorter. This is one of the leading explanations for why the planet has been speeding up. A quiet transaction at the center of the Earth paid out across the whole spinning world above it, showing up at the surface as a day that comes up short by a millisecond. It is worth dwelling on how intimate that connection is. The inner core and the surface are not directly touching. Between them lie thousands of kilometers of liquid metal and slow-flowing rock. And yet, through the magnetic and physical bonds that link these layers, a change in the spin of the deepest part of the planet can be felt, faintly, in the length of the day, measured at the surface. A person setting their watch, a navigation system timing, a signal, a financial network stamping a trade, all of them are, in a sense, reading the behavior of a solid iron ball thousands of kilometers beneath the ground. A ball no human eye has ever seen and no human hand will ever touch. The center of the Earth and the clock on your wall are part of the same connected system. But the iron heart is only one of the suspects. Because while something strange is happening at the center, something equally strange is happening to the field it generates. The magnetic shield is weakening. To appreciate why that should concern anyone, you have to understand what that shield actually does. The sun does not only send us light and warmth, it also blasts out a constant storm of charged particles, a searing wind of radiation streaming outward in every direction. And every so often, the sun unleashes something far worse. A violent eruption that hurls a wave of high-energy particles across space at staggering speed. These eruptions are among the most powerful events in the entire solar system, releasing in moments more energy than humanity has produced in its whole history. When one of them is aimed at the Earth, it can cross the gulf of space between the sun and our planet in a matter of days, or in the most violent cases, less than a single day. The particles arrive as an invisible tidal wave, slamming into the outer reaches of the magnetic field and sending it ringing and shuddering. Most of the time, the shield holds, and we experience nothing more than a brightening of the auroras. But the more violent the eruption, and the weaker the shield it strikes, the more of that energy can reach down toward the surface and the delicate technology that now blankets it. If that radiation reached the surface unimpeded, it would be devastating. It would strip away the upper atmosphere over time, fry the electronics we depend on, and bathe every living thing in a level of radiation that life is simply not built to withstand. We have a neighbor that shows us exactly what this fate looks like. Mars is roughly half the size of Earth, and long ago it almost certainly had a churning core and a magnetic field of its own, along with rivers, lakes, and a thick atmosphere. But Mars is smaller, and it cooled faster, and at some point in its distant past its internal dynamo faltered and fell silent. Without a magnetic shield, the solar wind began stripping its atmosphere away, molecule by molecule, across hundreds of millions of years. Today Mars is a frozen, irradiated desert, its air a thin whisper of what it once was, its water locked away as ice or lost to space entirely. That is the quiet warning written across the face of the red planet. A world can have everything it needs for a rich and living surface, and lose it, simply by losing the shield that comes from a restless metal heart. It is a sobering thing to look up at the red planet and understand that, in a sense, we are looking at a possible fate, a world that once had so much and held on to so little. The difference between a living world and a dead one can come down to something as hidden and unglamorous as whether a ball of iron at the center keeps churning. We rarely think about the core. We never see it, never feel it, never have any reason to consider it in the course of an ordinary day. And yet the entire habitability of the surface, the air we breathe, and the protection from the radiation overhead traces back to that distant, churning engine and to the field it throws out around the world. The magnetic field is what stands between us and that. Generated by the churning iron of the core, it reaches far out into space, deflecting the worst of the solar onslaught, channeling the dangerous particles around the planet and toward the poles, where they spend their energy harmlessly in the glow of the auroras. That shimmering curtain of light in the polar sky is the visible signature of the shield doing its job. When you look up at the auroras, the great rippling sheets of green and red that dance over the polar skies, you are watching the planet's defense system in action. Each shimmer is the energy of a solar particle being spent harmlessly high in the atmosphere, guided there by the magnetic field, far from the fragile life below. What looks like one of nature's most beautiful displays is, in truth, the glow of a battle, fought silently at the edge of space, every single day, between the fury of the sun and the shield generated by the iron heart of the world. We see only the most peaceful evidence of it, the soft light in the night sky, while the violence it represents passes us by unfelt. For as long as we have been able to measure it, that shield has been strong and reasonably steady. But over the last 2 centuries, since careful measurements began in the early 1800s, the global strength of the magnetic field has been declining. It has weakened by roughly 9% overall in that time. That figure deserves a moment of thought. Careful, systematic measurement of the field's strength only began around the early 1800s, when scientists first developed instruments precise enough to track it across the globe. In the relatively short span since then, a noticeable fraction of the field's strength has quietly drained away. Now, a decline over 2 centuries does not, by itself, prove that anything alarming is underway. The field has always risen and fallen, and a couple of 100 years is the blink of an eye against the timescales on which the core operates. But the rate of the decline, and the fact that it is steepest in one particular region, has made researchers pay close attention, because the field is not weakening evenly across the whole planet. And in one particular region, the decline is far steeper and far stranger. Stretching across the southern Atlantic Ocean and reaching over a large part of South America, there is a vast zone where the magnetic field is dramatically weaker than anywhere else on Earth. Scientists call it the South Atlantic anomaly. It is, in effect, a dent in the planet's armor, a region where the protective shield has thinned so much that the belts of trapped radiation surrounding Earth dip much closer to the surface than they should. This is not an abstract concern. Spacecraft passing through this region are exposed to noticeably higher levels of radiation. Satellites are routinely affected, suffering glitches and damage as they cross it, and many are deliberately programmed to power down their most sensitive systems while passing through, the way you might shield your eyes walking past a blinding light. Even the great orbiting laboratory where astronauts live and work has to account for it, the radiation spiking as it sweeps through that weakened patch of sky. There is a strange and telling detail about this region. Astronauts who have spent time aboard orbiting spacecraft have reported seeing brief, unexpected flashes of light, even with their eyes closed, when passing through this zone. Those flashes are high-energy particles, the very radiation the field is meant to deflect, punching through and striking the retina directly. It is a vivid, almost intimate demonstration of what a thinning shield actually means. The danger is not abstract. It is bright enough to see from the inside of a closed eye, and the anomaly is not staying still. It has been growing, deepening, and drifting slowly westward, and recent measurements suggest it may even be beginning to split into 2 separate centers. Watching it change from year to year is one of the clearest windows we have into the restless behavior of the field. A weakened patch that simply sat still might be dismissed as a fixed quirk of the planet's magnetism. But a patch that grows, deepens, drifts, and shows signs of dividing is a sign of something actively in motion below, a pattern in the molten metal that is itself evolving. Satellites dedicated to mapping the field in fine detail have tracked these changes closely, building a picture of a shield that is not static at all, but shifting beneath our feet in ways that have real consequences for the technology orbiting overhead. The cause traces all the way back down to the churning iron of the outer core. The magnetic field is not a smooth, simple thing. It is generated by an unimaginably complex flow of molten metal, full of swirls and eddies and reversals. And beneath the southern Atlantic, the flow appears to have organized into a pattern that locally weakens and even partly reverses the field above it. In other words, the dent in the shield is a window onto the turmoil far below. Deep beneath the southern Atlantic, researchers believe there may be a great churning patch in the liquid metal of the outer core, a region where the flow has organized in a way that drives the local field in the wrong direction, partly canceling the field that should be there. Some have linked it to an enormous structure sitting at the very base of the mantle, a vast province of dense, ancient rock that may be disturbing the flow of metal beneath it and shaping the field above in turn. Whatever the precise cause, the message is the same. The thinning of the shield over the Atlantic is not a surface phenomenon. It is the visible bruise left by something happening thousands of kilometers down, in the hidden engine of the planet. What is happening in the core is being written into the sky, and this raises a question that has hung over the field for a long time. Could the magnetic field be heading towards something far more dramatic than a localized weak spot? The planet's magnetic poles are not fixed. The North Magnetic Pole, the point your compass actually points toward, wanders constantly, and in recent decades it has been racing across the top of the world, sprinting from the Canadian Arctic towards Siberia at a pace that has forced scientists to update the official models of the field more often than ever before. And on far longer timescales, the field does something truly astonishing. The wandering of the North Magnetic Pole is itself a striking story. For most of the time people have been navigating by compass, the magnetic pole sat in the Canadian Arctic, drifting slowly, a manageable few kilometers each year. Then, in recent decades, it began to accelerate, picking up speed until it was racing across the top of the world towards Siberia at a pace far faster than anything in the historical record. The change was so pronounced that the official global model of the magnetic field, the one that guides ships, aircraft, and the navigation built into countless devices, had to be updated ahead of schedule because the pole had moved faster than the existing model had predicted. Something deep in the core had shifted, sending a surge through the flow of molten metal, and the pole above it lurched in response. It is yet another sign that the engine below is in a restless phase. It flips. The entire magnetic field of the planet reverses, north becoming south and south becoming north. This is not speculation. It is recorded permanently in the rocks. When molten rock erupts and cools, tiny magnetic minerals inside it lock into alignment with the field as it was at that moment, freezing a snapshot of the planet's magnetism into stone. Read those frozen snapshots across the ocean floor, layer by layer, and you find a striped pattern of reversals stretching back across millions of years. This discovery was one of the great revelations in the history of the Earth's sciences. As new rock wells up along the great cracks in the ocean floor and spreads slowly outward, it carries with it a permanent record of the magnetic field at the moment it cooled. The result is a vast natural tape recording, written in stone, with stripes of normal and reversed magnetism running parallel on either side of the ocean ridges. Reading those stripes, scientists could see the field flipping again and again across the depths of time, and could even use the pattern to measure how fast the ocean floor itself was spreading. The planet had been keeping a diary of its own magnetic history all along, and we finally learned how to read it. The field has flipped many hundreds of times in the planet's history. The flips do not come on a tidy schedule. Sometimes hundreds of thousands of years pass between them, sometimes millions. The last full reversal happened around 780,000 years ago, which means, by the rough rhythm of the past, we are arguably overdue. But overdue is a slippery word when it comes to the magnetic field. The reversals do not follow a clock or a calendar. They are the unpredictable output of a chaotic engine, and the long gaps between them are averages, not appointments. To say we are overdue is only to say that, looking at the typical spacing of past reversals, more time has passed since the last one than the average interval. It does not mean a reversal is imminent, and it does not mean one is even certain to come soon. The field could weaken for a while and then recover, as it has done many times before, in events where it dipped and rallied without ever fully flipping. Or the current weakening could be the early stage of a true reversal, the beginning of a process that will unfold across the centuries to come. There is simply no way, with what we know today, to be certain which it is. A reversal is not instant. It is a slow, messy process that may unfold across many centuries or even thousands of years, and during the transition, the field does not simply switch cleanly. It weakens, it tangles, it can briefly sprout multiple poles scattered across the globe, and its overall strength can drop to a fraction of normal before it rebuilds in the opposite direction. Imagine a world during such a transition. Instead of one north and one south, a compass might point toward any of several weak magnetic poles scattered unpredictably across the planet. The clean, simple shield we know today, shaped like the field of a bar magnet wrapping neatly around the world, would dissolve into a tangle of competing fields, weaker overall and far less effective at turning away the radiation from the sun. This confused, diminished state might persist for centuries before the field finally reorganizes itself, settling once more into a simple shape, but with north and south swapped from where they began. The auroras, normally confined to the polar regions, might appear at unfamiliar latitudes, dancing over places that have never seen them. It would be a strange and unsettling chapter in the planet's history, though not, in itself, a catastrophe for life. It is important to be clear and calm about what this would and would not mean. A magnetic reversal is not an extinction event. The fossil record shows no clear pattern of mass die-offs lining up with past reversals. Life has weathered hundreds of them. The planet keeps turning. The atmosphere does not blow away. The reason is that even a tangled, weakened field still offers some protection, and the atmosphere itself provides a great deal more. The thick blanket of air above us absorbs much of the radiation that does break through, which is why life on the surface has come through past reversals largely unscathed. The creatures of those ancient eras went on living, breeding, and evolving through the whole long transition, very likely without ever sensing that anything had changed at all. The fossil record simply does not show waves of extinction marching in step with the flips of the field. But our ancestors lived through those reversals as hunters and gatherers, with nothing electronic to lose. We would live through it wrapped in a fragile web of satellites, power grids, and delicate machines, all of which are vulnerable to exactly the kind of radiation a weakened field lets through. We already have a glimpse of how vulnerable that web can be, even with the field at full strength. In the late summer of the year 1859, the sun unleashed one of the most powerful eruptions ever recorded, striking the Earth. The charged particles slammed into the planet's magnetic field and set the whole sky alight. Auroras, normally confined to the far polar regions, blazed across the sky as far south as the tropics, so bright in places that people woke believing dawn had come early. And the young telegraph networks of the age, the most advanced technology of their day, went haywire. Sparks leapt from the equipment. Lines failed. Some operators reported their machines sending and receiving messages even after the power had been disconnected, driven by the electric currents the storm had induced in the wires. That storm struck a world that ran on little more than telegraph wires. A storm of the same scale today would strike a civilization utterly dependent on satellites, power grids, and electronics woven into every corner of daily life. The damage could run into staggering sums and take years to fully repair. Transformers that take many months to build could be knocked out across whole regions. Satellites could be damaged or lost. Communication and navigation networks could be disrupted for an extended time. The systems that move money, route aircraft, and keep the lights on all lean, in one way or another, on electronics that a powerful enough storm could overwhelm. This is not a hypothetical that lives only in the distant past. Storms nearly as powerful have brushed past the planet in recent decades, missing a direct strike by a matter of days in the planet's orbit. It is a reminder that the shield over our heads is not a guarantee, and that the technological civilization we have built sits exposed beneath a sometimes violent sun. Now imagine such a storm arriving during a period when the planet's shield was weakened and tangled, partway through a great reversal. So the weakening we are measuring now, the deepening dent over the Atlantic, the racing pole, the long-term decline, may be nothing more than ordinary restlessness in a system that is always restless. Or it may be the early stirring of one of those grand reversals, the field beginning the long, slow process of turning itself inside out. The honest answer is that nobody knows for certain. What we do know is that the shield is weakening, the core is changing, and the two are unmistakably connected. And while the deep interior reshapes the planet from within, the surface is being reshaped from above by something far more visible and far more immediate. The ice is melting. At the top and bottom of the world and across the high mountains sit enormous reserves of frozen water built up over countless thousands of years. The ice sheet covering Greenland and the far larger one covering Antarctica together hold the overwhelming majority of the planet's fresh water, locked away as ice kilometers thick. These are not static slabs. They are slow, living rivers of ice, constantly creeping toward the sea under their own colossal weight, breaking off into icebergs at their edges, and, in balance, being replenished by fresh snowfall inland. The scale of these frozen reserves is difficult to take in. The ice covering Antarctica reaches, in places, more than 4 kilometers thick, burying entire mountain ranges beneath it, hiding lakes and landscapes that no eye has ever seen. If you could stand at its center, you would see nothing but a white plain stretching to every horizon, with kilometers of solid ice beneath your boots. This ice did not form overnight. It is the compressed snowfall of hundreds of thousands of years, each year's snow pressing down on the layers below, squeezing them into dense ice that preserves, deep within it, tiny bubbles of ancient air, samples of the planet's atmosphere from ages long past. To melt such a thing is to undo the patient work of an almost unimaginable span of time. For a long time, that balance held, roughly. What melted away was roughly matched by what fell as new snow. But that balance is broken. The great ice sheets are now losing mass, year after year, far faster than fresh snow can replace it. Greenland has been shedding hundreds of billions of tons of ice every year. Parts of Antarctica, particularly in the west, are doing the same, with vast glaciers accelerating their slide toward the ocean as the warming water eats away at the ice shelves that once held them back. These ice shelves deserve a moment of attention because they play a role most people never consider. Where a glacier meets the sea, it often extends out over the water as a floating tongue of ice, sometimes stretching for tens of kilometers. These floating shelves act like a cork in a bottle or a buttress against a wall, holding back the far greater mass of ice piled up on the land behind them. When the warming ocean thins these shelves from below, or when they crack and break apart, the cork is pulled from the bottle. The land, ice behind them, no longer held in check, begins to flow toward the sea faster, sometimes far faster. This is why scientists watch the great glaciers of western Antarctica with such unease. Some of them rest on bedrock that lies below sea level and slopes downward inland, a configuration that, once the retreat begins in earnest, can feed on itself and become very difficult to stop. The reason for this lies in the shape of the land beneath the ice. When a glacier sits on bedrock that slopes downhill away from the sea, every step of retreat exposes a deeper, thicker face of ice to the warm ocean water. That deeper face melts faster, which pulls the glacier back further, which exposes an even deeper face, and so the retreat can accelerate on its own, without any further push. This is the kind of self-reinforcing process that keeps scientists awake at night, because once it crosses a certain threshold, slowing it down or reversing it may no longer be possible on any timescale that matters to us. A handful of these great glaciers hold enough ice between them to raise the world's oceans substantially, and their behavior in the coming decades is one of the largest open questions in the science of the changing planet. The most obvious consequence is the one everyone knows. The water has to go somewhere, and it goes into the sea, raising the level of the oceans across the entire planet. This rise does not happen evenly, and it does not announce itself with drama. It creeps upward by millimeters each year, a pace so slow that from one day to the next nothing seems to change at all. But the slow creep adds up. And along low-lying coasts, where hundreds of millions of people live, the difference between the sea of a century ago and the sea of today is already being felt. High tides reach a little farther inland. Storm surges, riding atop a higher baseline, push deeper than they once did. Salt water begins to seep into freshwater supplies and farmland near the coast. None of it is sudden. All of it is relentless. And the great ice sheets hold enough frozen water that, were they ever to release the bulk of it across the coming centuries, the map of the world's coastlines would have to be redrawn. But there is a second consequence, far less obvious and far stranger, and it ties this melting ice directly back to the spinning of the world. When ice melts at the poles and that water spreads out across the oceans, it is not just adding volume to the sea. It is physically moving mass around the planet. It is taking enormous weight that used to be concentrated at the poles, near the axis the Earth spins around, and redistributing it outward, toward the equator. To understand why the location of that weight matters so much, return once more to the spinning skater. Mass held close to the axis of rotation barely affects the spin. Mass flung far from the axis affects it enormously. The poles sit almost exactly on the planet's spin axis, the still points at the top and bottom of the turning world. The equator, by contrast, is as far from that axis as it is possible to be on the surface of the Earth. So when ice that has been sitting frozen near the poles melts, and that water spreads across the world's oceans, much of it ends up far from the axis, bulging out around the planet's middle. Weight is being carried from the still center toward the spinning edge. And remember the figure skater. When the skater pulls their arms in, close to the spin axis, they speed up. When they push their arms out, away from the axis, they slow down. The planet works the same way. As meltwater carries mass away from the poles and out toward the bulging middle of the world, it is, in effect, the skater extending their arms. It nudges the planet to spin a little slower, lengthening the day, which leads to a genuine and fascinating tension at the heart of all this. The deep core seems to be trying to speed the planet up. The melting ice is trying to slow it down. These two forces are pulling in opposite directions, and the day length we actually measure at the surface is the running total of that tug of war, along with the shoving of the atmosphere and the sloshing of the oceans. It is a kind of contest playing out across the whole body of the planet, from its molten heart to its melting poles to the winds in its sky. On any given day, one influence may gain the upper hand, and the day runs short. On another, a different influence pushes back, and the day runs long. What the atomic clock's record is never one single cause, but the sum of all of them at once, the net outcome of a competition with no clear end in sight. For now, the core appears to be winning, and the planet is spinning faster. But the contribution from melting ice is growing every year, and some scientists argue that without it, the planet would be spinning faster still. In other words, the melting ice is quietly masking just how much the deep interior is accelerating the world. This creates a strange and almost hidden situation. The acceleration we measure at the surface is not the full strength of whatever is pushing the planet faster. It is the net result, the leftover, after the slowing effect of the melting ice has been subtracted from it. If the ice were not melting, the days would be shorter than they already are. The deep interior may be pushing harder than the numbers suggest, with the surface melt acting as a partial brake that hides the true force of the engine below. To untangle these competing influences, to say exactly how much of the change comes from the core, how much from the ice, how much from the oceans and the air, is one of the hardest problems in the field. Every contribution must be measured, modeled, and carefully separated from the others, and the answer shifts as new data arrives. It gets stranger. Moving all that mass around does not only change how fast the planet spins, it changes the very axis it spins around. Every spinning object has an axis, an imaginary line it turns about, and for the Earth, that line runs roughly between the geographic poles. But that line is not perfectly fixed. It drifts in a slow, looping wander as the distribution of mass on and within the planet shifts. This is called polar motion, and it has always happened, gently, driven by the seasons and the oceans and the slow flow of the interior. For more than a century, scientists have tracked the slow, looping wander of the pole, watching it trace small circles and drift gradually in one general direction. It is an exquisitely sensitive measurement because the pole responds to the movement of mass anywhere on or within the planet. A shift in the great ocean currents nudges it. The seasonal swelling and shrinking of the ice and snow nudges it. The slow churning of the molten interior nudges it. The pole is, in effect, a needle that registers the changing distribution of weight across the entire world. But in recent decades, the wandering of the pole has changed direction noticeably, and scientists have traced a large part of that shift directly to the redistribution of water from melting ice. Let that settle for a moment. Human-driven melting of the ice sheets has measurably changed where the axis of the entire planet points. We have, without ever intending to, given the world a tiny nudge, and the spin axis has responded. The amount is small, measured in meters at the poles, not kilometers, and it poses no direct danger to anyone. But the significance of it is profound. It means that the collective weight of human activity in melting the ice has grown large enough to leave a fingerprint on the orientation of the entire planet in space. For most of history, the idea that humanity could influence something as vast as the axis of the Earth would have seemed absurd, the stuff of myth rather than measurement. And yet here it is, recorded in the data, a quiet line that traces the moment our influence reached planetary scale. There is a strange dignity, and a strange weight in that single line. It does not threaten anyone. No one will ever feel the axis shift or notice the pole drifting a few meters in a new direction. But as a measurement, it marks a threshold that humanity crossed without ceremony or even awareness. For the first time, the cumulative actions of our species grew large enough to register in the orientation of the entire planet against the fixed stars. We have always shaped our local surroundings, our fields and forests and rivers. Now we have, however faintly, shaped the spinning of the world itself. The ground beneath us, the ice above us, and the iron at our center are all part of a single connected system, and pull on any one thread, and the others move. And there is one more great system woven through all of this, vast, powerful, and now showing signs of strain. The ocean currents. The oceans are not still. They are in constant, planet-wide motion, driven by wind, by the spin of the earth, and by differences in temperature and saltiness from one region to another. These currents form an immense, interconnected loop, a global conveyor belt of water that carries heat from the warm tropics toward the cold poles, redistributing the sun's energy across the entire face of the planet. This conveyor is not a single current, but a vast, connected system, winding through every ocean on Earth. Water that sinks in the cold north travels for centuries along the deep ocean floor, creeping through the dark, finally rising again to the surface in distant seas on the far side of the world. A single drop of water might take more than 1,000 years to complete one full circuit of this great loop. It is the slowest, grandest circulation on the planet, moving more water than every river on Earth combined, and it has shaped the climate of entire continents for as long as the oceans have existed in their present form. When this conveyor is healthy and strong, climates stay within the bounds that civilizations have come to depend on. When it falters, those bounds can shift. One arm of this system is particularly important and particularly famous. In the Atlantic, warm, salty surface water flows northward from the tropics, carrying an extraordinary amount of heat with it. As it travels north and cools, it grows denser, and eventually it sinks, plunging into the deep ocean and beginning a long, slow return journey south along the floor of the Atlantic. This sinking is the engine that helps keep the whole conveyor turning. This northward flow of warmth is the reason that the western edge of Europe is far milder than its latitude alone would suggest. Cities that sit as far north as the frozen wilderness of Canada enjoy gentle, temperate climates. Kept warm by the heat, the ocean ferries up from the tropics. It is, in a very real sense, a central heating system for an entire continent. The scale of the heat being moved is almost impossible to imagine. The warm waters flowing north carry an amount of energy that dwarfs the entire output of every power station humanity has ever built, many times over, delivered steadily, day and night, year after year, without pause. This is why a city perched at a high northern latitude, which by rights should sit frozen and locked in ice for much of the year, instead enjoys green fields, mild winters, and gentle rain. The ocean is quietly ferrying tropical warmth thousands of kilometers across the planet and laying it down along distant northern shores. Take that delivery away, and the gift of warmth would vanish with it. But that system depends on a delicate balance, and that balance is being disturbed. When the great ice sheets melt, they pour enormous quantities of fresh water into the northern Atlantic. Fresh water is less dense than salty water, and that flood of lighter water makes it harder for the surface flow to grow dense enough to sink. If the sinking slows, the entire conveyor slows with it. And the measurements suggest that this is exactly what is happening. there is a grim feedback hidden in this process. As the conveyor weakens, it carries less warm, salty water north, which changes the conditions in the Northern Ocean, which can further disrupt the delicate balance that drives the sinking. A weakening can, under the wrong conditions, encourage further weakening. Scientists watch for these self-reinforcing loops with particular care because they are the mechanisms by which a slow, gradual change can tip over into a faster, harder-to-reverse one. The conveyor has been measured directly for only a few decades, with arrays of instruments strung across the Atlantic to gauge the flow. But longer records, read from ocean sediments and other natural archives, allow scientists to place today's measurements in a much deeper context. The Atlantic circulation appears to be weakening, and some studies indicate it may now be in its weakest state in well over 1,000 years. The consequences of a serious slowdown would be far-reaching and, in places, sharply counterintuitive. While the world as a whole continues to warm, the regions that rely on that northward heat delivery could actually grow colder as the supply of tropical warmth falters. Weather patterns across entire continents could shift, rainfall belts could move, and storm tracks could change. The lands that today receive gentle, reliable rains might find them arriving at different times or in different amounts, throwing long-established patterns of farming and life out of step. Regions accustomed to mild winters could face harsher ones, even as the planet as a whole continues to warm, a paradox that captures just how counterintuitive these large-scale shifts can be. The point is not that any single dramatic outcome is certain. It is that a system which has held remarkably steady for thousands of years, and which entire ways of life have quietly come to depend on, is showing signs of strain, and a strained system is a less predictable one. The system that has helped keep the climate of whole regions stable for thousands of years could reorganize itself in ways that are difficult to predict and slow to reverse. The geological record tells us this is not idle speculation. In the deep past, this same circulation has slowed and even shut down before, and when it did, the climate of the lands around the northern Atlantic changed with startling speed. Evidence locked in ice cores and ocean sediments shows that, at the end of the last great ice age, the northern regions plunged back into bitter cold within the span of a single human lifetime after the conveyor faltered. The warmth returned later, just as abruptly, when the circulation recovered. These were not gentle, gradual shifts spread across centuries. They were sharp, rapid reorganizations of an entire climate system, flipping from one state to another in years to decades. The mechanism behind these abrupt flips is exactly the kind of self-reinforcing feedback that makes the conveyor so worth watching. A surge of fresh water from melting ice could weaken the sinking, which weakened the conveyor, which cooled the north, which changed the ice and the winds, which fed back into the circulation once more. Once such a loop took hold, the system could swing rapidly to a new state and hold there, sometimes for centuries, before swinging back just as fast when conditions shifted again. This is the unsettling character of so many of the planet's great systems. They can be stable for a very long time, absorbing pressure without much apparent change, and then cross a threshold and reorganize with startling speed. The slow accumulation of change does not always produce slow consequences. That is the unsettling lesson buried in the sediments. The great ocean conveyor does not always change slowly and politely. Sometimes it changes its mind in a hurry, and an entire hemisphere feels the result. And here, finally, all the threads begin to gather, because the slowing of the ocean conveyor is driven by the melting ice, and the melting ice is shifting the spin and the axis of the planet, and the spin is being wrestled in the opposite direction by the changing core, and the core is the same place that generates the weakening magnetic field. Each of these stories, told on its own, is striking. Told together, they start to look less like a set of coincidences and more like a single planet quietly entering a period of change across every one of its great systems at once. Stand back far enough, and a shape begins to emerge from all these separate observations. A planet whose deep interior is shifting, changing the spin of the whole world and weakening the shield that protects it. A surface losing its great reserves of ice, which raises the seas, moves the planet's mass, nudges its axis, and slows the ocean currents. An atmosphere responding to all of it, its winds and weather patterns shifting in turn. No single one of these is the whole story. They are facets of one interconnected system, each influencing the others, all moving together in the same window of time. And that is exactly the conclusion the data has been pushing scientists toward. In research institutions that study the deep behavior of the planet, a particular kind of picture has become more and more common over the last several years. It takes the independent measurements from each of these systems, the rotation, the core, the magnetic field, the ice, the ocean currents, and the wandering axis, and it lays them all out on a single shared timeline. When you do that, something stops looking like noise and starts looking like a pattern. The rotation anomaly, measured against the calm baseline of the 1990s, shows a clear departure beginning around the years 2009 and 2010. Strengthening through the middle of the 2010s, estimates of the motion deep in the core show a shift beginning in roughly the same window. Each of these signals has its own personality, its own pace, its own degree of certainty. Some are measured directly, with instruments reading the quantity in question. Others are inferred, reconstructed from related measurements and careful modeling. Some emerge cleanly from the background. Others must be teased out from a great deal of noise. A careful scientist treats each one with the appropriate caution, neither overstating its precision nor dismissing its meaning. But when they are laid side by side, the caution does not erase the pattern. The surface acceleration of the spin emerges clearly from the background around the year 2016, with its most extreme values arriving in the years 2020 through 2022. The loss of ice from Greenland shows a step change increase, beginning around the year 2012, and it has only steepened since. The weakening of the field over the southern Atlantic shows a steeper decline emerging through the middle of the same decade. The retreat of Arctic sea ice shows its sharpest, sustained decline beginning around the year 2012. Notice how these dates cluster, drawn from systems that could hardly be more different from one another. The loss of ice is a matter of temperature and melting at the surface. The weakening of the field is a matter of churning metal thousands of kilometers down. The retreat of sea ice is a matter of ocean and atmosphere at the top of the world. These are not phenomena that anyone would expect to share a timetable, and yet their major departures fall within the same handful of years. That convergence is exactly what makes the pattern so striking and so difficult to wave away. And the weakening of the Atlantic circulation accelerates through the middle of the 2010s as well. When you place these timelines beside one another, the eye is drawn to a single stretch of years, somewhere around the start of the previous decade, where line after line begins to bend away from its long, calm history. It is as if the planet, having held a steady note for thousands of years, quietly changed key, and every instrument in the orchestra shifted at once. Some shifted a little earlier, some a little later, each with its own character and its own pace, because each system responds to a disturbance in its own way and on its own timescale. But the clustering is unmistakable. These are not 7 separate stories that happen to be unfolding at the same moment by chance. They have the look of 7 different voices, all responding to the same underlying change. Each of these measurements was made independently, different instruments, different institutions, different scientific communities that, in many cases, rarely talk to one another. And yet each one shows its major departure from the historical baseline within the same single decade. The chance that 7 separate planetary systems all broke from their long-term patterns within the same window, purely by coincidence, with no shared underlying cause, is not exactly zero, but it is very, very small. Coincidences happen, of course. Any one of these signals, on its own, might be dismissed as a passing fluctuation, the kind of wobble that any complex system produces from time to time. 2 of them lining up might be chance. But 7, each measured separately, each departing from a long and stable history within the same single decade, strains the idea of coincidence past any reasonable breaking point. When that many independent witnesses tell the same story, the simplest explanation is no longer that they all happen to be mistaken in the same way at the same time. It is that they are all describing, from their different vantage points, the same underlying event. What it suggests instead is that these systems share a common excitement, that something shifted in the deeply connected machinery of the planet during that window, and that the shift then rippled outward through layer after layer, surfacing in the spin, in the ice, in the field, and in the sea. There is real debate about where the root of it lies. Some researchers place the deepest cause in the core, arguing that a change in the flow of the molten metal set everything else in motion, altering the spin and the field together. Others point to the surface, to the warming that is melting the ice, reshaping the oceans, and shifting the atmosphere, with the deeper signals being responses rather than causes. Still others suspect that the truth is a tangle of both, that surface and depth are coupled more tightly than we once believed, each capable of nudging the other. The honest position is that no one yet knows for certain which thread to pull first. What nearly everyone agrees on is that the threads are connected and that the planet is behaving across multiple systems at once in a way it has not during the era of careful measurement. This is not a constructed story laid over the facts. It is what the data itself shows when you simply place it side by side. And the lesson buried in the geological record is sobering in its own quiet way. When multiple planetary systems enter a phase of departure together, they do not snap back quickly. They tend to stay in that departed state for decades, sometimes centuries, before settling toward a new balance. The planet does not flick a switch from one steady state to another. It moves through long, restless transitions, periods in which the old equilibrium has been left behind, but a new one has not yet been found. During such times, the systems that make up the planet hunt for a new arrangement, overshooting, correcting, and overshooting again, like a pendulum slowly finding its rest. These transitional periods can stretch across far more than a single human lifetime, which means that anyone living through the beginning of one has no way of seeing its end. We may be standing near the start of just such a transition, with the steady world of the recent past behind us and the shape of the next equilibrium still unknown. And the balance they finally settle into is not identical to the one they left. That is perhaps the single most important idea in all of this. The new equilibrium is not the same as the old one. When the planet finally settles, it does not return to where it started. It finds a new arrangement, a new balance point, with the ice in a different place, the seas at a different level, the currents in a different pattern, the field in a different shape. The world that emerges on the far side of a transition is recognizably the same planet, but not the same in its details. And it is precisely in those details, the level of the sea along a coast, the timing of the rains over a region, the strength of a current that warms a continent, that human life has made its home. The planet is not broken. It is not dying. life has survived transitions far more violent than this, across hundreds of millions of years. Far greater swings in climate, far larger reversals of the field, far more dramatic upheavals of ice and ocean. The planet has always changed, and it has always endured. In its long history, the Earth has been a frozen ball of ice from pole to pole, locked in a deep freeze so total that even the tropics may have frozen over. It has been a steaming hothouse, with no permanent ice anywhere, and forests growing near the poles. It has been struck by mountains falling from the sky, drowned by floods of lava that covered areas the size of continents, and scoured by ice ages that came and went dozens of times. Through every one of these upheavals, life persisted, adapted, and eventually flourished again in the new conditions. After the greatest catastrophes, when whole groups of living things vanished, life did not simply end. It reorganized, filled the empty spaces, and in time produced forms more varied and remarkable than what came before. The planet has a deep resilience written into it, a capacity to absorb tremendous shocks and continue turning, continue supporting life, continue changing. That resilience is real, and it is worth holding on to when the scale of these changes feels overwhelming. The planet does not need our protection to survive. It will keep turning, keep changing, keep finding new balances, long after every question we are asking today has been answered or forgotten. But human civilization was not built to ride out a planetary transition. It was built during a rare and precious stretch of calm. Think of the timing of it. For most of the planet's history, and even for most of the history of our own species, the world was a more turbulent place, swinging in and out of ice ages, with seas rising and falling by enormous amounts and climates lurching from one state to another. It was only in the last several thousand years, after the most recent ice age loosened its grip, that the planet settled into the unusual steadiness that allowed us to plant the first crops, build the first cities, and begin the long climb toward everything that followed. Civilization is, in a very real sense, a creation of the calm. It could not have arisen during the turbulence, and it has never had to endure a genuine planetary transition. We have no memory, as a civilization, of what it is to live through one, because we have never had to. The roughly 10,000 years since the last great ice age retreated have been astonishingly quiet by the standards of geological time. The spin stayed within a narrow band. The field was relatively steady. The ice retreated at a manageable pace. The seas rose and then settled. This stretch of calm was not guaranteed. It was, in the grand sweep of the planet's history, an unusually gentle interval, a rare lull between more turbulent times. And it is no accident that everything we recognize as civilization, agriculture, cities, writing, science, the entire human story of the last several thousand years blossomed precisely within this window of stability. We are, in a sense, children of the calm. We grew up believing the world was steady because, for the brief span we have been paying attention, it largely was, and in that stillness, we built everything. We built cities at the very edge of the sea, on the unspoken assumption that the sea would stay where it was. We launched a web of satellites on the assumption that the planet would turn predictably. We wired the world with power grids and financial systems and hospital networks on the assumption that the clock would always run smoothly forward. We built navigation systems on the assumption that the poles would hold their place. Every great structure of the modern age carries within it a quiet assumption about the steadiness of the planet. The engineer who designs a coastal city assumes the sea will stay roughly where it has always been. The architect of a global network assumes time will always move forward at a predictable pace. The builder of a power grid assumes the rhythms it is tuned to will not wander. None of these assumptions were foolish. They were the only reasonable assumptions to make, drawn from the entire span of recorded experience, in which the planet had indeed been steady. The trouble is not that anyone was careless. The trouble is that the experience we drew from covered only a brief, calm chapter, and the planet appears to be turning to a new page. Every one of those assumptions is now being tested at once. Not catastrophically, not all in a single moment, but steadily, and in a direction that puts a slow, rising pressure on systems that were designed for a calmer world. This is the quiet nature of the challenge. It does not arrive as a single dramatic event with a clear before and after. It arrives as a gradual tightening, a steady accumulation of small mismatches between the world our systems were built for and the world that is actually emerging. A few more centimeters of sea here, a few more milliseconds of drift there, a little more radiation leaking through the thinning shield, a little less warmth delivered by the slowing currents. None of it is a catastrophe on its own. All of it together, applied without pause over years and decades, is a steadily growing strain on the structures we have built and the assumptions we built them on. So the real question, the one that sits at the center of every model and every data set and every late-night discussion in the laboratories that study this, is not whether these changes are happening. They are. It is not even whether they are connected. They appear to be. That much the data has made increasingly clear year after year, as the separate threads have been laid side by side and found to share the same window of time. The reality of the changes is not in dispute among the people who measure them. The connection between them is strongly suggested by everything we can see. The question is how fast the transition will unfold, and whether these tangled, feeding-back systems will settle into a new balance within the span of a few decades, or keep accelerating. And the difference between those two futures is enormous. If the planet finds a new equilibrium within a generation, the engineering problems are large but solvable. The corrections are finite. The institutions that maintain the infrastructure of the modern world have enough time to adapt, to redesign, to reinforce. In that future, the changes are a challenge to be managed rather than a crisis to be survived. Coastal defenses can be raised over decades. Timekeeping systems can be rebuilt to handle a faster planet. Power grids and navigation networks can be hardened against a more restless field. The pace of the change stays within reach of our capacity to respond, and humanity adapts to a somewhat different world without ever facing a moment of true reckoning. But if the feedbacks keep amplifying, the window for calm, managed adaptation narrows. The corrections needed begin to grow faster than they can be put in place. The systems with the least slack fail first, and their failures put strain on everything connected to them. This is the quiet danger of a tightly woven world. When everything depends on everything else, a disturbance does not stay contained. A failure in one system becomes a stress on the next, and a stress on the next becomes a failure of its own, and so the trouble can travel, hopping from one connected piece to another faster than anyone can respond. The very efficiency that makes the modern world so capable, the way each part leans on all the others, is also what makes it brittle when the conditions it was built for begin to shift beneath it. A planet in transition does not need to deliver a single great blow to cause harm. It only needs to keep applying steady, patient pressure to systems that were designed assuming the pressure would never come. Neither future is certain. And the most honest thing the researchers closest to the data can say is that the uncertainty is larger now than it was a decade ago, not smaller. This is a strange and important point. We tend to assume that more measurement and better science should steadily shrink our uncertainty, narrowing everything down toward a single, confident answer. In many ways, it has. We know far more about each of these systems than we did a decade ago. But the deeper understanding has uncovered a complexity that was hidden before, a web of connections so intricate that predicting the behavior of the whole has become harder, not easier, even as our grasp of the individual parts has improved. We have traded a simple ignorance for a sophisticated uncertainty, which is, in its own way, a kind of progress, though it offers little comfort. More watching has produced more evidence of change. Better models have produced sharper views of the mechanisms, and those sharper views have revealed just how tightly everything is bound together, which means just how easily a change in one part can drive changes in all the others. This is, in a way, the deepest lesson of the whole story. For a long time, scientists studied these systems largely in isolation. One field studied the spin of the planet, another studied the magnetic core, another the ice, another the oceans, the atmosphere, the wandering axis. Each built its own models, its own instruments, its own understanding. And only as those separate understandings grew sharp enough did it become clear how thoroughly they are woven together, how a tug on the core can be felt in the length of the day, how the melting of ice can move the very pole the planet turns about. The closer we look, the more connected it all becomes. And the more connected it becomes, the harder it is to say with confidence what any single change will ultimately bring. The planet you live on is not a fixed stage that the human story plays out upon. It never was. It breathes, it shifts, it moves through cycles that dwarf the whole of recorded history on timescales that make our oldest monuments look like things built yesterday. The pyramids, which feel ancient to us, are younger than a single wobble of the pole. The whole of written history, every empire and every age, fits inside a span shorter than the interval between two beats of the inner core's slow rhythm. We experience the planet as fixed and eternal because our lives are so brief beside it. A human lifetime is a blink against the time scales on which the Earth truly operates, far too short to feel the great slow processes turning beneath us. And so it is easy to mistake the calm of our own moment for the permanent condition of the world. But the calm is just a frame from a much longer film, and the film is still running. What is happening now is not outside the range of what the Earth does, but it is outside the range of what the Earth has done during the brief, calm window in which we have been here to notice. And so the deepest question, the one that hides beneath all the others, the one written into the rotation of the world, the wandering of the pole, the thinning of the shield, and the melting of the ice, is also the simplest. How fast? How fast are we moving toward the new balance? And what will that balance look like when we arrive? Everything hinges on the pace. A change that unfolds slowly enough can be met, adapted to, lived with. The same change arriving too quickly can outrun our ability to respond. The destination may matter less than the speed of the journey toward it, because it is the speed that decides whether we arrive prepared or overtaken. And the honest truth is that the pace is the one thing the science cannot yet pin down, because it depends on how all these coupled systems feed back into one another in the years ahead. A question whose answer is still being written. That answer is not in a textbook. It is being written right now, in the turning of the planet beneath your feet, in the drift of ice you will never see, and in the churning of iron nearly 3,000 kilometers below the chair you are sitting in. The instruments are running. The data is coming in, day after day, more precise than ever before. Around the world, in quiet laboratories and observatories, the measurements continue without pause. The atomic clocks tick. The radio telescopes track the turning of the planet against the distant stars. The satellites map the weakening field. The instruments on the ice weigh what is being lost. The arrays strung across the ocean gauge the strength of the great currents. Every day, the picture grows a little sharper, the record a little longer, the understanding a little deeper. We are not watching from the outside. We are aboard the very thing we are measuring, riding the spinning planet as we track its spin, living on the changing surface as we record its change. And for the first time in the long history of the world, there is a species living on its surface that can watch it change in real time and understand, even a little, what it is seeing. That, in the end, may be the most remarkable part of the whole story. For 4.5 billion years, the planet sped up and slowed, flipped its field, melted and froze, and rearranged its oceans, with no one to notice and no one to care. The changes simply happened, recorded only in stone and ice, waiting to be read by eyes that did not yet exist. And now, in this thin sliver of time, there are minds that can measure the spin of the world to a fraction of a millisecond, listen to earthquakes echo through its iron heart, map the weakening of its invisible shield, and weigh the ice vanishing from its poles. We are the planet's first witnesses. Whatever transition is now underway, we are the only generation that has ever been able to watch it unfold and grasp what it means. Every generation before us lived on the same restless world, but blind to its deeper motions. They felt the earthquakes and watched the auroras and saw the seas, but they had no way to know that the iron heart was turning at its own pace, or that the field was weakening, or that the day itself was changing length by fractions of a millisecond. They lived inside the great slow processes without ever being able to see them. We are the first to hold the full picture, or at least the first to begin assembling it, to see the spin and the core and the field and the ice and the oceans as parts of a single connected whole. It is an extraordinary thing to be alive at the exact moment when a species first gains the ability to read the deep behavior of its own planet. That is not a reason for fear. It is a reason for attention, and for a certain kind of awe. There is wonder in it, if you let yourself feel it. The same planet that has carried life through billions of years, through ice ages and reversals and upheavals beyond counting, is still doing what it has always done, still turning, still changing, still alive in the deep geological sense. We are not watching a machine break down. We are watching a living world move through one of its phases, the way it has moved through countless phases before. Only this time with witnesses present to record it and minds present to wonder at it. To understand even a fraction of that, to read the spin and the field and the ice as parts of one connected story, is among the most remarkable things our species has ever managed. The planet is not ending. It is turning a page. And we happen to be alive at the exact moment the chapter changes. There is something humbling in that, and something thrilling too. We did not choose to be born into a moment of transition, just as the people of the long calm did not choose their stillness. But here we are, equipped as no generation before us has ever been, with instruments that can feel the planet move and minds that can begin to understand what they are sensing. The story of the changing Earth is being written in real time, in the turning of the world and the drift of the ice and the churning of the iron beneath us. And for the first time, there is someone here to read it as it is written. Thank you for taking this journey to the center of our restless world. If it left you seeing the ground beneath you a little differently, like the video, and subscribe, and we will see you on the next journey into the cosmos.